Welcome to this explainer. Today, we're tackling a really fundamental challenge in modern machine learning. We're looking at exactly how models manage to uncover hidden structures buried inside massive, messy datasets. I mean, millions of data points are generated every single day, right? Making sense of all that raw information is exactly what we're focusing on today.
And this brings us to a huge fundamental question. When data is meticulously labeled by a human, say you have a picture that is explicitly tagged as a cat, supervised learning models know exactly what to do with it. But what happens when we just have raw, unlabeled data? How do machines actually find patterns in data without human labels? Okay, let's dive into this.
Here is our roadmap for today. First, what is clustering? Second, the clustering workflow. Third, k-means explained. Fourth, evaluating results. And fifth, the deep learning evolution. Section 1. What is clustering? And finding the hidden structure.
So the absolutely crucial point here is that clustering is an unsupervised machine learning technique. It groups unlabeled examples based entirely on their similarity to one another. Imagine a healthcare system with tens of thousands of patients. By grouping patients with similar symptoms and treatment responses, we can simplify millions of complex data points down into a single manageable cluster ID. We do the exact same thing for YouTube videos based on viewer demographics and watch history. This cluster ID acts as incredible data compression, saving a ton of computational resources. And beautifully, it also helps preserve privacy, because instead of passing individual, highly identifiable user histories into a model, we can just pass a generalized cluster ID.
Moving right along to Section 2, the clustering workflow, which is essentially our recipe for success.
You can think of this workflow like a really strict recipe. Step 1, prepare your data. Step 2, create a similarity metric. Step 3, run your clustering algorithm. And Step 4, interpret those results and adjust. I literally cannot stress this enough. You could have the most flawlessly designed algorithm in the world, but if your raw data ingredients aren't prepped correctly in Step 1, your final result is going to completely fail. Now, to calculate similarity, your features must share the exact same scale. If your data forms a nice, standard Gaussian bell curve, you just normalize it using z-scores to find the standard deviations from the mean. But if your data is messy and lacks a known distribution, you'll want to default to quantiles. This basically divides your dataset into intervals containing equal numbers of examples. Just keep in mind, to use quantiles effectively, you really need at least 10 times n examples. If you don't have enough data, just stick to normalization. Which brings us to Section 3. K-means explained. This is our foundational solution. Once your data is prepped, you need an algorithm, and k-means is super popular because it scales linearly. Its complexity is big O of n times k. That just means its runtime won't totally explode as your datasets hit the millions. And the loop itself is brilliantly simple. First, we provide a guess for k, that's the number of clusters, and the algorithm drops k random centroids into our data. Step 2, it assigns every single data point to its nearest centroid. Step 3, it looks at that newly formed cluster and recomputes the mathematical center, moving the centroid to that new mean position. Finally, it just repeats steps 2 and 3 over and over. The centroids keep shifting to the center until nothing moves anymore. It converges. It's like a giant puzzle solving itself. But wait, actually, how does the algorithm know what is nearest or most similar? Well, as a quick refresher on manual similarity, we basically combine feature data into a single numeric value. Imagine a dataset of shoes with two numerical features, size and price. After scaling the data, we calculate the root mean squared error, or RMSE. By doing this math, the algorithm can objectively distance a size 8 shoe costing $120 from a size 11 shoe costing $150. Next up is Section 4, evaluating results. This is our reality check. Here's the tricky part about clustering. Because it's an unsupervised learning technique, we don't have a labeled ground truth to easily verify our work against. So we have to rely on heuristics to figure out if our model actually did a good job. We do this by comparing two crucial metrics. First is cluster cardinality, which is simply the number of examples inside a cluster. We weigh that against cluster magnitude, the sum of the distances from all points in a cluster to their centroid. Intuitively, these two should grow together. If you add more points to a cluster, the total distance of those points to the center should go up, right? So if we plot these two metrics and spot a cluster where the cardinality and magnitude aren't growing together proportionally, boom, we know we've found an anomaly that needs investigating. Now, what's really interesting about this is how we solve the headache of manually choosing k, our number of clusters. We use something called the elbow method. If we plot out our total distance, or loss, against an increasing number of clusters, the loss naturally drops. But eventually that drop becomes super marginal. We are looking for the elbow in the graph, the point where the slope first makes a drastic change. Looking at this data, an optimal k-value is clearly sitting right around 11.
Even with neat tricks like the elbow method, k-means definitely has some distinct disadvantages. As we just saw, you still have to manually choose k. It's also incredibly sensitive to random initial centroid placements, and the centroids can easily get dragged way out of place by outliers. But the absolute biggest flaw? It suffers horribly from the curse of dimensionality. As the number of dimensions in our data goes up, distance-based similarity measures start to break down. The distances between all examples mathematically converge, meaning k-means just can no longer distinguish what is similar and what isn't.
To solve that, we enter Section 5, Deep Learning Evolution, Neural Nets for Clustering.
When datasets become wildly complex with hundreds of features, we kind of have to abandon manual math entirely. We pivot to deep learning. Enter the next evolution, embeddings. Instead of manually combining features, we train a deep neural network to reduce our complex features into lower dimensional vector representations. The real beauty of these embeddings is that similar examples, say 2 YouTube videos covering similar topics and watched by the same users, naturally end up physically closer together in this mathematical space. It's a real game changer. To actually generate these embeddings, we generally use one of 2 supervised tools. Autoencoders predict their own input, forcing the data through smaller hidden layers to learn a compressed representation. Alternatively, we use a predictor when one specific feature is absolutely paramount. For instance, if predicting house price is what matters most, we use price as our label and extract the embeddings from that trained network. Just remember, you have to remove your label from the input data or you're gonna get label leakage.
Okay, once we have our embeddings, we need to mathematically compare them. We can use Euclidean distance to check the physical distance between vector ends. We can use cosine similarity, which focuses purely on the angle between vectors and completely ignores their length. Or we can use the dot product. Now, the dot product focuses on both angle and vector length. This is absolutely crucial for things like recommendation engines because in embedding space, length often correlates with popularity. So if you want your cluster to factor in how popular a video is, you definitely have to use the dot product.
All right, let's wrap this up. Summary, clustering review.
Let's quickly recap our core takeaways. First, data prep is non-negotiable. You've got to scale your data using z-scores or quantiles. Second, k-means is a really popular, fast algorithm, but it heavily struggles with outliers and high dimensions. Third, you can visually find your optimal k using the elbow method. And finally, when manual feature combinations fail you, deep neural network embeddings step in to automate complex similarity measures. It's cool to see how each tool we discussed today evolved directly to solve the limitations of the previous one. Before we go, I want to leave you with this provocative thought. As our real-world datasets continue to grow exponentially more complex and the dimensions of our data just multiply, will foundational manual algorithms like k-means actually survive the decade? Or are deep neural embeddings the singular, undeniable future of machine learning? Thank you so much for joining me on this explainer. Keep exploring, keep questioning, and I'll see you next time.